So I like to start with some pieces of advice, and you've heard these before, but I think it's important to remember this. Do problems. And in this part of the course, this is all about really hitting that geometry. Do you understand the setup? Because the majority of the challenge for the integration is not the integrals themselves, it's getting the bounds right, or switching between different coordinate systems. That's all about geometry. How do you get better at it? You do problems. The more problems you do, the more natural things will become. Also, as always, please take care of your health. That includes physical health, get out, do some exercise, get enough rest. Also includes mental health. There's a lot of stressors right now. We're getting near the end of the semester. Make sure you're doing okay. Well, let us begin. And we'll start with a simple problem. Well, maybe. Evaluate the following. We're going to integrate 1 to e, integrate log y to 1, cosine of e to the x minus x dx dy. Now, this problem just says integrate, and our first reaction is like, oh, well, there's nothing so crazy here. And then we look a little bit closer and we might say, see, cosine of e to the x minus x, you really can't integrate that. Not because I don't think you're good, it's just because you can't integrate it. Nobody can. And I know you might say, well, I'm very creative. I'm sure I could come up with something. No. That's not. Don't be creative. The calculus is not a time to let your inner creativity shine. No. Be systematic. Be precise. So you might say, okay, here's sort of a clue. So this problem has a clue embedded into it. It says, look, you can't integrate cosine of e to the x minus x with respect to x, but we could do it if we were doing the integral with respect to y. So we're going to change the order of integration. And this is an important skill to have, because it's going to take an integral that we can't do to an integral where we can at least do one step. So our first chance to do this, and we will have many chances today. So when we're looking at changing the order of integration, we want to understand the bounds. So remember that the outer integral goes with the outside d, so this tells us that y is going to go between 1 and e. Then the inner integral goes with the inner d. So it tells us that x is going to go from log y up to 1. Now, probably the curve we have to figure out is this curve x equals log of y, but this is not such a bad curve because this is the same curve as y equals e to the x. You say, okay, that's going to give us some idea what's going on. So you have y equals e to the x, which shows that, and x equals 1. Well, that's somewhere. Let's say here. Here's x equals 1, y equals e to the x, and we're going between y equals 1, which is here, and y equals e. Now, it turns out that e to the 1 is e, so it means that we're going from there. So between any value of y, between 1 and y, we're going from this curve, y equals e to the x, or x equals log y, and we're going out to 1. So this is how we're currently integrating, as we're slicing horizontally that region. So if we're going to change our order of integration, what we're going to do is we're going to change essentially the way we slice. So we're going to now slice vertically. So I say, okay, figure out where x goes from. X goes 0 to 1. And what about y? Well, for any y value, we're going to go from the bottom line, would be the line y equals 1, up to the top, well, that's y equals e to the x. So it's 0 to 1, 1 to e to the x. So now we've done our change of order. So remember, whenever you change order, you've got to update the bounds. That's the big idea here. The bounds are probably the biggest part of this exam. And so if you're pretty good at getting the bounds right, you'll do pretty well. So now we can integrate with respect to y. Integral 0 to 1, cosine of e to the x minus x times y, because this is essentially a constant. We evaluate y equals 1 to y equals e to the x dx. So this becomes 0 to 1. And we should suspect, if we're actually asked to evaluate this, that somehow when we evaluate this inner integral, that nice things happen. Well, what's happened is we've picked up this e to the x minus 1 term. Now, if we put on our Calc 1 hats, which it wasn't that long ago that we did Calc 1, we would say, this looks like a substitution. If you let u equal e to the x minus x, du would be e to the x minus 1 dx. So, we say, aha, that's exactly what we're going to do then. So this is going to become the integral of cosine of u du. But we've got to do our bounds. So plug in 0. E to the 0 minus 0 is 1. E to the 1 minus 1 is e minus 1. The integral of cosine is sine. So sine of u, evaluated from 1 to e minus 1, which gives us sine of e minus 1, subtract sine of 1, also known as our final answer. Really can't do much beyond that. And there you go. What a fun problem. So these are the types of problems where, be aware. You might need to be able to change your order of integration. And we may not always tell you to do that. So how do you know when to do it? Well, basically, if you have an integral you can't do, change the order. You got to go in the order that you can do. Number 2. Let R be the region square root of y squared less than or equal to x, less than or equal to the square root of 1 minus y squared. Find the integral over this region of x over x squared plus y squared plus 1 dA. Okay, well, let's see if we can't figure out what this region looks like. So there's 2 pieces here to this region. So we have one part, this square root of y squared less than or equal to x. Now, square root of y squared is just a fancy way of saying the absolute value of y less than or equal to x. So if you were to sketch x equals the absolute value of y, it looks a lot like the absolute value function, except you've just turned it on its side. So that's absolute value of y equals x. And we want to have x be to the right of that. So that's what the x greater than or equal to the absolute value of y says. So I want to be over in this part. There's this other piece. X is less than or equal to the square root of 1 minus y squared. Well, if we were to look at x equals the square root of 1 minus y squared, that's x squared plus y squared equals 1, because you square both sides, add the y squared, which tells us that what's going to happen here is there's going to be a circle, in fact, a circle of radius 1, the unit circle. So this is the curve x equals the square root of 1 minus y squared, and we want to be to the left of that. So our region is the region as follows. It's this piece here. All right, so there's our region that we have. Now, what do we want to do? Well, we want to integrate over that region. And looking at this problem, we say, this problem, we should switch to polar. Now, what's the clue of polar? So polar, you're looking for 2 things to suggest polar. One thing you're looking for is a region which is very simple in polar. And this is a region which is very simple in polar. If you look at the angles here, you have this angle coming down is negative pi fourths. This angle coming up is positive pi fourths. And this circle here, that's the unit circle, that's the circle r equals 1. So in polar coordinates, this is a very easy region to describe. In fact, much easier than it is to describe in rectangular coordinates. Now there's another clue that says polar coordinates should be good, and that is in the function itself. There's this part, x squared plus y squared. When you see x squared plus y squared, that becomes simpler if you switch into polar because it becomes r squared. And what happens is you're going to reduce the number of plus signs in your denominator. And every time we can knock out a plus sign, that is a good thing. because that makes our problem easier to do. So this is a polar problem. And again, notice we never said at the beginning, switch to polar. You just figure it out based upon what the problem is asking you to do. All right. So here we go. We're going to integrate. X, well, what we do is we use our formulas. X is r cosine theta. Y is r sine theta. And of course, x squared plus y squared equals r squared. So our function will become r cosine theta over r squared plus 1. dA becomes r dr d theta. Theta goes from negative pi fourths to positive pi fourths. R goes from 0 up to 1. So now we're ready to do this integral. And this integral is a nice integral. This is one of those integrals you can actually split into two integrals and handle the two pieces separately. So I can do the integral from negative pi fourths to positive pi fourths of cosine theta, d theta. And then I can do the integral from 0 to 1 of the r's. Now there's an r and a second r here. Don't forget, that r in the r dr d theta, very important r, so don't forget about it. R squared over r squared plus 1 dr. So the first integral of cosine, that's sine. Negative pi fourths to positive pi fourths. We'll come back to that. Okay, how do you integrate r squared over r squared plus 1? Do you know? What can you do? Well, one thing you can do is you can say, well, if you remember to Calc 2, there was long division. You could actually divide r squared plus 1 into r squared. But here's something pretty simple to do. R squared plus 1 minus 1. Still r squared. R squared plus 1 over r squared plus 1 is 1. Then minus 1 over r squared plus 1 dr. So this becomes r minus arctangent of r. Evaluate that from 0 to 1. And if you plug in 1, you get 1 minus arctangent of 1, pi fourths. And when you plug in 0, you get 0. Come back here, we should evaluate this. So we'll get sine of pi fourths, which is root 2 over 2. Subtract sine of negative pi fourths, which is negative root 2 over 2, which means that from this piece we'd get a root 2. So if you put it all together, our final answer is square root of 2 times 1 minus pi over 4. And there you go. That's it. Okay. Number 3. Set up, but do not evaluate, the sweetest sentence. An integral that finds the surface area of the surface z equals x squared y plus x e to the y over the region where y squared is less than or equal to x is less than or equal to 4. So we're going to think about this here, this x squared y plus x e to the y. This is our f of xy. So the surface area, well, the way you find that is you integrate over your region the square root of 1 plus f sub x squared plus f sub y squared dA. So that's how we do it. And so there's not so much to do. Once you have the formula, everything else will be pretty much straightforward. Probably the one thing we do need to figure out is what our region is. So let's sketch that. We have y squared less than or equal to x. So x equals y squared is a sideways parabola. So we have our x equals y squared. And x equals 4 is a vertical line. So our region will look something like this. So from here we say, oh, well, the best way to describe this probably is just to use what we already have. We already know where x goes from. So we know that x is going between y squared and 4. So if we do horizontal slicing, all we have to figure out is what range of y's do we have. And to do that, we say, well, when does y squared equal 4? And the answer is at plus minus 2. So we can go between negative 2 and 2 for y, and then x can go from y squared to 4. So now we're ready to put it together. So integral, square root of 1 plus, take the derivative with respect to x. We get 2xy plus e to the y squared, plus, take the derivative with respect to y, x squared plus x e to the y squared. And now, the way we talked about our region is a dx dy. Y goes from negative 2 to positive 2. X goes from y squared to 4. And that's our surface area. Nice. Boy, hopefully we'll have something like that. That's a fun problem. Okay, next problem. Number 4. Let S be the solid where x is greater than 0, y is greater than or equal to 0, z is greater than or equal to 0, and we're bounded by the surfaces z equals x and z equals 1 minus y squared. So this is a picture. And it says, set up the integral of f of x, y, z dv. It really should say integral over our solid S. There was an S I forgot to put there. Where a, dv is in a particular order, dy, dz, dx, and b, where dv goes dz, dx, dy. So let's work through and see what's happening here. Now, let's try to understand these two surfaces. There's actually slightly different colors here. So the one that's green, where's that coming from? Well, if you look here in the yz plane, so if you label our axes here as x, y, z, in the yz plane, we see it's this curve down. Well, this corresponds to 1 minus y squared. It's this sort of upside down parabola. Z equals 1 minus y squared. So our green surface, that's z equals 1 minus y squared. Now, what about the blue surface? The blue surface, where's that? Well, look at where it hits. It hits the xz plane, and you see this line, that corresponds to z equals x. So this is the plane z equals x. So that's that surface. Now, you might notice that this actually has two other bounding surfaces, but we can't see them right now because they're on the back sides. So one bounding surface over here, that is the yz plane, also known as x equals 0. And the other bounding surface is the xz plane, also known as y equals 0. So those are our bounding surfaces. Those are the ones we're going to be interacting with as we play with these bounds here. So, where to begin? Well, let's just start with part A. So, dv equals dy, dz, dx. So when I'm thinking of setting up bounds, the way I like to set up bounds is I like to do the following, is I like to say, look, my outermost layer, so if I'm thinking of these as 3 layers, the outermost layer is between 2 numbers, then 2 curves, and the innermost is 2 surfaces. So I like to do the surfaces last. That's just my preference. Some people like to do surfaces first. So if I'm doing surfaces last, let's suppose I'm working on part A. I'm going to look down the y-axis. So as I stare down the y-axis, what do I see? Well, the answer is I don't see the y-axis anymore. It's just going to become a single point. So the y-axis becoming this point. What I will see is I'll see the xz plane. And so, what does that look like? Well, it looks like this triangle that we see here. So I have this line coming out, and then here I have z equals 1. And that's the triangle that I see as I look down the y-axis. So now, that can help me get my bounds figured out. So integral, integral, integral. Then I have my same function, f of x, y, z, dy, dz, dx. So I start with my x, and I say, okay, where does x go from? Well, according to the picture, I need to see these two curves intersect here. Z equals x, z equals 1 would correspond to x equals 1. So x is going from 0 up to 1. Now, suppose I know x. Where does z go from? So if I have an x value, z goes between two curves. So I want two curves of the form z equals something. So I need to say, okay, where do I go from? Well, z equals x to z equals 1. So I write that as x, 1. Now we come to the inner layer, which is y. So now we go back to our three-dimensional picture, and what's happening here is we're integrating with respect to y, which means we should think about moving parallel to the y-axis. So we're moving back and forwards here, left and right, if you will. So what happens is when I integrate with respect to y, the back side is that back triangle, that xz plane. Then I move forward until I hit this front curved slope. So I see that my bounds are going to be those two surfaces. And I need them in the form y equals. Well, the start, that's no problem. That's y equals 0. Then I'm coming to this front plane, which is z equals 1 minus y squared. Well, I need to rewrite that. So 1 minus y squared, I need to solve for y, because I need a y equals, since it's a dy. So y squared equals 1 minus z. So y will be the square root of 1 minus z. And that goes there. And so there is our integral for part A. So we're going to do something similar for part B. It's going to be different, but the process will be the same. So the difference is now we're looking down the z-axis. So I'm looking down the z-axis, and what do we see? Now this is a little bit more interesting because it's not completely obvious what we're going to see right away. So one of the things to figure it out is certainly as I look down the z-axis, what we'll see is we'll see something in the xy plane. That's okay. That's pretty convincing. The other thing that we can convince ourselves of is that this line segment here, that's going to project down. Okay. So that's one thing. That's our shadow, we'll see. That's going to have the same length as it did up here. It had length 1 up there. So we're going to have a line segment, it hits at 1. But the question is, this curve here, where they meet, where is that going to project down to in terms of the xy plane? Because it's going to vary. It's not going necessarily straight down. It's somewhat curved. So this is our shadow, if you will, in the xy plane. The good news is, it's not as bad as I'm making it sound. Because what do we have? Well, I need to figure out when do z equals x and z equal 1 minus y squared intersect. Well, put these together, you get that 1 minus y squared has to equal x. Or, if you rearrange it, y squared is equal to 1 minus x. There you go. So, finally, that tells us what? Well, it tells us that y is the square root of 1 minus x. Not that we necessarily need it in that format, but, you know, if it helps, it helps. Okay. So, that's a square root. It's actually a square root that's going backwards. It starts here, and it works back up. So, here's the curve, y equals square root of 1 minus x, or if you like, this is also the curve x equals 1 minus y squared. So if you look at it as x equals 1 minus y squared, that's a parabola that opens to the left, but then you've shifted it. So there's our region in the xy plane. So we're ready to start setting things up for part B. Our integral f of x, y, z And our order is dz, dx, dy. So we start by saying, what happens to y? Well, we should figure out where it intersects. That's not so bad. When x equals 0, y will be the square root of 1. So that says we're at 1. So y goes from 0 to 1. So that's our outer layer, 0 to 1. Where does x go from? Well, x is going to go between these two curves. So I'm going left to right. So I'm going to go from x equals 0 to x equals 1 minus y squared. So 0 to 1 minus y squared. Where does z go from? Well, now we go back to our 3D picture. And so we come back to our 3D picture, and we say, all right, if I'm looking at dz, I want to move parallel to the z-axis. I'm going to be moving up, down, up, down. So I can imagine I come up, and then I hit this first plane, the blue plane, then I go up until I hit the green plane. So what are my bounds? Well, I'm going from the blue, which is z equals x, up to the green, which is z equals 1 minus y squared. And we're done. That's it. So once you have a picture, it really helps to understand what's happening. It really helps, of course, if you have a picture. We always give you a picture. But if we don't give you a picture, there'll be curves not too dissimilar for this. We're not going to give you anything too crazy. Things that you can understand. So draw a picture. Think about what's happening. If you're integrating with respect to x, you got to move in the parallel to the x-axis. Integrating with respect to y, moving parallel to the y-axis, so forth and so on. Look down an axis to help simplify, to get those outer bounds. With practice, these get better. So we should probably practice a little bit more, because number 5 kind of has a similar feel. All right, rewrite the following as a single integral. Ooh, one integral. See, currently we have 2 integrals. So there's an integral from 0 to 1, integral 0 to 1, integral 0 to 1 minus y, in the order dx, dz, dy, and then there's 0 to 1, 1 minus x to 2 minus x, 0 to 2 minus x minus y, dz, dy, dx. So these are 2 different integrals. And what we want to do is somehow say, no, we can mush these together and form a single integral. So we want to get sort of a picture here. So we're going to work on drawing a 3-dimensional picture. Once we have the 3-dimensional picture down, then we'll be able to put things together and life will be good. So let's draw a set of axes here for reference. And our picture will probably become a bit convoluted by the time we finish it, but hopefully we'll try to keep it pretty clean as we get there. So let's see what this says. Here we're told that the outer layer tells us that 0 is less than or equal to y is less than or equal to 1. And then the next layer says that 0 is less than or equal to z is less than or equal to 1. Well, that's pretty useful. That tells us what? It tells us that if you come into our picture, x, y, z, that we really have a 1 by 1 square sitting in the yz plane. So I'll come over here to the yz plane. I'm going to sort of sketch in loosely right now a 1 by 1 square. So there's our y goes from 0 to 1, z goes from 0 to 1. The last innermost layer says that 0 is less than or equal to x is less than or equal to 1 minus y. Well, x equals 0 is in fact the yz plane. So that says the back side is this surface. So we're going to start from here, and then the front side is a surface. So again, because I'm in the innermost layer, that's the surface. What surface is it? It's the surface x equals 1 minus y. Now, that might not look like a surface. In fact, it looks a lot to us like a line. X plus y equals 1. And so we're probably thinking, how is that a surface? Well, first off, let's talk about what that line is. It's the line in the xy plane. It would hit the y-axis at 1. It would also hit the x-axis at 1. So in terms of the xy plane, it's a straight line. Now, how does it become a surface? Well, the answer is, what you do is it's the same thing up and down in the z direction. When there's no z aspect, you just copy it up and down. So what we end up with is a shape. That's the surface is this plane. It's perpendicular, if you will, to the xy plane. So the first integral, it's kind of an interesting shape. It's kind of like an inclined ramp, but you've turned it on its side. Because it's an inclined ramp that's been turned on its side. So that's why it's kind of like it. Okay, so that's the first integral. Okay, now let's go to the second integral. So for the second integral, let's read off what that one says. Well, again, outside says 0 less than or equal to x, less than or equal to 1. So we're only going from 0 to 1 for x. That's good, because that's where the first one goes between. That's a good sign. Y goes from 1 minus x to 2 minus x. So 1 minus x less than or equal to y, less than or equal to 2 minus x. Now, we can actually think for a second about what's going on here. We talked about y equals 1 minus x. If we look at that, that's the same line that we've mentioned before, x plus y equals 1. So you're going from this line x plus y equals 1 out to a different line, namely this line y is 2 minus x, which you can rewrite that as x plus y equals 2. So x plus y equals 2 is similar, but instead of starting here at 1, it comes out here to 2. And then we just run parallel. So here we are. We're going parallel line. X plus y equals 1. X plus y equals 2. We're only x going between 0 and 1. So there's our two-dimensional region from our two outer layers. Now we come to our last part. So our last part says 0 less than or equal to z, less than or equal to 2 minus x minus y. Now z equals 0, that's easy. That's the xy plane. So it actually does start down here where it's been marked. So what about this other one? Z equals 2 minus x minus y. Well, that happens to be the same as z plus x plus y equals 2. It's a plane. Now we start thinking about, okay, where are some points on the plane? Now there's a couple of points that we might be interested in. This corner, that'll be a point, because this is at the point 1, 1, 0. This point over here, this is really at the point where? It's at 0, 2, 0, so that's a point on the plane. What about this point? Well, where would that be? Well, that's at the point where x equals 0 and y and z are both 1. 0, 1, 1. That's the point on the plane. So we now have 3 points on the plane. And how about this point? Well, that would be the point where we have x is 1, and then y is 0, and z is 1. So this is also a point on the plane. So we actually have 4 points on the plane. And so the nice thing is these all hook up in a nice way. So what we end up with is this plane here. All right, so now we kind of have our shape. So we had this inclined ramp, we turn on its side, and now we have another ramp, but it's sort of been skewed in some way to form this shape. So it's time to think about, all right, we want to set this up as a single integral. We have our basic pieces, and we just have to figure out how to put our pieces together. So I'll mark the various planes here. This is x plus y plus z equals 2. We have this top part here. This was at z equals 1. Over here, this little side piece here is x equals 1. Then we have our bottom, which is the bottom side here. That's our plane z equals 0. This back side over here, that's y equals 0. And this other back side, I'll put it over here, that's our x equals 0. So we have a bunch of pieces coming together, but all the pieces that bound this region are flat, which is a good thing. We like flat things. We have a pretty good track record with flat things. So we have a couple of choices. We got to choose our order of integration so it can be done in one integral. So one thing we might say is, okay, could we have it so that our z is the innermost layer consistently? Well, the challenge is, think about moving up and down with z. If I'm over here, I have this top part as z equals 1, but then if I come over here, the top part is this other plane. So z equals 1, just integrating the inner part with z is a bad choice because we have different surfaces on top. That's not going to work. What if, say, our innermost integral with respect to x? Could that work? Well, unfortunately, not all the time. Because say you pick a point over here and you move back and forth with x, then you're fine. But if I'm all the way over here, I'm moving between two other surfaces. So the bounding surface changes if we integrate our last layer with respect to x. Well, that's going to sort of narrow us down a little bit. It's not with respect to x, because our bounding surface changes. It's not with respect to z, our bounding surface changes. So by process of elimination, and we probably should have suspected this when we started, given that here was x, here was z, the final answer better have it as f of x, y, z, dy. And now, okay, what about the last part? So let's look down the y-axis. If you look down the y-axis, what do we see? So if we're in the y-axis, we'll see the xz plane. The y-axis is actually the origin right there. And what do we see? The square, yes. So that is nice. We like the square. And really, it doesn't matter which order we take the square in. So we'll go dy, dx, dz. So we say, all right, the square. It's not just any square, by the way. It's a 1 by 1 square. So we have that z goes 0 to 1. X goes 0 to 1. Where does y go from? Well, we're going to go back and forth. So we start at the square on the back side, which is y equals 0, and we move forward until we hit the plane. This plane, x plus y plus z equals 2. Solve for y, because it's in terms of dy, so it's a y equals. So you get y equals 2 minus x minus z. And that is the answer. Woohoo! Good stuff. Good stuff. Okay. I will say that these problems are the ones I think students struggle a lot with. And if you are one of those students, practice. There's lots of old problems that involve three-dimensional pictures. The more you practice, the better you get. All right, number 6. Find the center of mass of the upside-down cone, 0 less than or equal to z, less than or equal to 1 minus root x squared plus y squared, with the density function is equal to x squared plus y squared squared. Now, there's a couple of things about this problem that are suggestive about how we should approach it. Namely, we see a lot of x squared plus y squared floating around. When you see things with x squared plus y squared floating around, you think, okay, if it's a 2D problem, I go to polar. If it's a 3D problem, I go to cylindrical. So we're going to do this using cylindrical coordinates. So remember that cylindrical coordinates, the way that it works is that it's polar plus z. So we're going to do what we would do with polar coordinates, but then we have this sort of extra z floating around. Now, as far as the shape goes, it's not too hard to get a sketch. We already even are told our basic shape. It's an upside-down cone. So a cone, that's our basic cone looks like z equals r. And so in 3 dimensions, it looks something like this. Well, the minus r, that turns it upside down. So that would have it going straight down. The 1 minus r Well, what you've done is you've added 1 in the z direction, so that shifts your cone up. So it starts, so the peak is at 1. And where does the bottom go? Well, we want it to go, the bottom is z equals 0, which is the xy plane. So our picture here of our shape is, we can sketch, we have a cone starting at 1 and coming down to the xy plane. So there's our cone. Our density function, we switch to x squared plus y squared, being r squared, so it's r squared squared, so it becomes r to the 4th. We have to describe our region in terms of our coordinate system. So because we're fully symmetric all the way around, in other words, around the z-axis, you could spin it. And this, by the way, is sort of an indicator that you want to think about using cylindrical coordinates, is when you have that rotational symmetry around the z-axis. So we get 0 less than or equal to theta, less than or equal to 2 pi. What about r? Well, r, you think about where's the biggest part? It's down here at the base. When z equals 0, you get 1 minus r equals 0. So it says that down here in the xy plane, it's a circle of radius 1. So we're going to go 0 less than or equal to r less than or equal to 1. And where does z go from? Well, it's already here. It's given to us. 0 less than or equal to z less than or equal to 1 minus r. So we have to find the center of mass. Now that tells us we got to find a lot, because you got to find x bar and y bar and z bar. But on a lot of these problems, you can save yourself some work, because this shape has symmetry around the z-axis. And by symmetry, it means if you spin it, nothing changes. And when I talk about nothing changes, I'm including the density in that statement. The density doesn't change if we spin. So if the density isn't changing, what that means is that the center of mass has to be on the x-axis. Well, sorry, not the x-axis, the z-axis, which tells us x bar and y bar are 0. So we're 2/3 the way to our answer. And it feels like we've barely just begun. Well, to be fair, we've done the easy 2/3. Okay, so I suspect that the next 1/3 might take us a while. So let's set up our mass. So we start by doing mass. And what is that? Well, that's the integral of density. It's a triple integral. That's another integral sign. Okay. Triple integral of density dv. Notice that for your things like mass, your moments, your momentum, which is inertia, they all have the same feel. It's always either a single integral or a double integral or a triple integral. For mass, you integrate density. For moment, distance times density. We'll do a moment in a moment. And then for inertia, distance squared times density. So for us, we have integral 0 to 2 pi for theta, integral 0 to 1 for r, integral 0 to 1 minus r for z, and then we're going to have our density, which is r to the 4th, and then we're going to do r dz dr d theta. This r is part of our dv, so don't forget it. It's important. So we integrate with respect to z, and what do we get? Well, there's no z, so it becomes r to the 5th times z from z equals 0 to z equals 1 minus r dr d theta. So that becomes 0 to 2 pi and 0 to 1 of r to the 5th minus r to the 6th, because you plug in z equals 1 minus r, you multiply it out. Then we're going to do that dr d theta. And we can actually do the d theta integral separately, because there's nothing that depends on theta on the inside. We integrate the d theta integral, so I'll move the d theta over to here. that would be 2 pi. And then we're going to have 1/6 r to the 6 minus 1/7 r to the 7th. Evaluated from 0 to 1, which becomes 2 pi. And you get a common denominator here would be 42. So you get 7 minus 6 over 42, so that's 2 pi times 1 over 42, or pi over 21. All right, that is not our answer. That's our mass. We need another part. What's our other part? Yeah, we need the moment to get our z bar. So we're going to do a moment, and our notation is xy plane. So we put xy. So whatever you put as a subscript here, that indicates the distance to that object. So here xy means xy plane. You could just do like x, and that would be x-axis, so forth and so on. Okay, so moment with respect to the xy plane, that would be integral z times your density dv. So our integrals are very similar. In fact, the only thing that happens is that we have the same setup, but now there's a z in there. So we get r to the 5th times z dz dr d theta. So this will be a little bit more exciting because now we have something to integrate with respect to z. So integral 0 to 1, and here we'll get 1/2 r to the 5th z squared. And we're going to evaluate from z equals 0 to z equals 1 minus r dr d theta. Well, we can again do what we talked about before, where really we can do the d theta integral separately. So if you move the d theta over here, there is no theta. So what does that give us? That's 2 pi. Then there's the 1/2, which I'll just put there. And then there's this integral from 0 to 1. So I have to square z squared. So 1 minus r squared would be 1 minus 2r plus r squared. But I'm multiplying by r to the 5th. So it would be 1 times r to the 5th minus 2r times r to the 5th. So that's 2r to the 6th plus r squared times r to the 5th, which is r to the 7th. And that's going to be dr. So this becomes pi. Makes you wonder why I chose this problem. I'm not sure why either. All right. 1/6 r to the 6th minus 2/7 r to the 7th plus 1/8 r to the 8th from 0 to 1. At least the good news is when you plug in 0, you get 0. So you plug in 1. So what does that become? Well, pi, and then you get 1 over 6 minus 2 over 7 plus 1 over 8. Now, if you were thinking, let's put this over a common denominator. Okay, that's one idea. Common denominator would be what? Well, I need something which is divisible by 6 and 7 and 8. So in this case, it would be 3 times 7 times 8. Because 3 times 7 times 8, 7 divides it, 8 divides it, and because of the 3 and the 8, 6 divides it. So what do I need to get from 6 to 3 times 7 times 8? Well, I need 7 and 4 more, so that needs 28. Here, 7, I need 24 more, so I need to subtract 2 times 24, which is 48. And the 8, well, I need 3 and 7, so I need 21. 21 plus 28 is 49. Subtract 48 leaves us with 1 over 3 times 7 times 8. Okay, now what's z bar? We haven't found it yet, but z bar, you take your moment, which is pi, over 3 times 7 times 8, divide that by your mass. 21, 3 times 7. So the pi's cancel. This becomes 3 times 7 over 3 times 7 times 8. or 1 over 8. So there's your z bar. And I guess we should say that our true center of mass, you should list all three coordinates, 0, 0, 1/8. It's a lot of work to get to 1/8. But, in some sense, it's like, oh, that's kind of a pretty answer. Now, you should always ask yourself a question, is this a reasonable answer? And by reasonable, you would say, okay, if I'd gone like a negative number, definitely not reasonable, because everything is above or equal to 0. But let's think about it. Okay, even though it's between 0 and 1, does it make sense that I should be near the bottom? And the answer is, well, yeah, because there's really a lot more weight near the bottom, because the weight gets better the further away you get from the axis. And the parts near the bottom, that's the parts where you see more stuff away from the axis. So you should definitely be biased towards the bottom. So this is a fairly reasonable answer. So that's our answer. Good. Whew. All right, that might be the most technically, well, maybe arithmetically demanding one. All downhill from here, right? Maybe. Number 7. Find the mass of the three-dimensional solid where z is greater than or equal to 0, x squared plus y squared is greater than or equal to 1, x squared plus y squared plus z squared is less than or equal to 2. And the density is given by the density of xyz is 2 over x squared plus y squared plus z squared. Now, if you look at the pieces here, there's a couple things. Z greater than or equal to 0, what that translates into is I am above the xy plane. So I'm up above the xy plane. X squared plus y squared greater than or equal to 1. Now, a lot of people would say, oh, x squared plus y squared equals 1. Isn't that a circle in the xy plane? And it is. But when you go to 3 dimensions, what does it become? It becomes a cylinder, because you just copy that up and down in the z direction. So we want to be greater than or equal to 1, which means I really want the parts out here. So again, I want to be above the xy plane. I want to be outside of the cylinder. Now we come to this last part. X squared plus y squared plus z squared less than or equal to 2. Well, x squared plus y squared plus z squared equals 2 is a sphere. And it's a sphere of radius root 2, and we want to be less than or equal to 2, which means we want to be inside the sphere. So what we do is we start piecing these pieces together. We say, okay, I need to be above the plane. I got to be outside the cylinder, inside the sphere. And what we come up with as the conclusion of what this shape looks like is it's got to do something like the following. I have this sphere here that comes down. I'm on top of the plane. And then there's this circle that's coming through. Or I really shouldn't say circle, I should say the sphere that's coming through. And we're getting sort of the outside part of it. So that's our shape. You could think of it as, one way to think of it is you took a hemisphere, and then you drilled a cylinder right down the middle. So we have our basic shape. Now, say, okay, we have our shape, sure, but how do we actually go about doing this problem, integrating it? So we have to think about our method. Now, we know the way to find mass. Mass, it's a basic formula. We've already talked about it. So to find mass, what we would do is we would integrate our density over our solid. So what's missing here is we've got to figure out the right setting to do it in. So this problem does not feel very Cartesian coordinate-y. It doesn't really feel like it's set up that way. So why not? Because this is not a function where we have things in terms of planes and boxes. No, it's just not right. It's just not right. Cylindrical coordinates is an option. I mean, there is a cylinder, but there's a better thing to try here, and that is spherical. Now, what's the clue that spherical is the good choice? Well, there's a couple of things. First off, there's a sphere. That's a pretty good sign that spherical coordinates are a good choice. But there's something else here. Notice this x squared plus y squared plus z squared. When you see a problem which has x squared plus y squared plus z squared, that's a strong indicator that you should be thinking spherical coordinates. Now, what does x squared plus y squared plus z squared become in spherical coordinates?
Rho squared.
Rho squared. Yes, you got it. See how elegant that is? There's no plus downstairs. It just whoosh, collapses. Perfect, perfect. So we are going to definitely go with our spherical direction. Now, there's a couple of things you have to remember about spherical. We'll get to the fun musical part in a moment. We got to describe the region in terms of spherical. Now, part of it is theta. Theta does the same thing as it does in cylindrical coordinates. What's happening as you spin around the z-axis? Because we have our nice all the way around, this will have 0 less than or equal to theta less than or equal to 2 pi. Now, to get an idea for rho and also for phi, I find it's best to work in a slice. So I imagine I'm going to slice down. So where I'm doing it almost like a half plane, where it's half of it is on the z-axis. So it's like a page where I have the z-axis, and then I'm coming out from the z-axis. So I like to call this r. Now what's going to happen is that this cylinder is going to show up at r equals 1. That's our cylinder of 1. And when you, of course, you spin this around, that forms your cylinder. The sphere becomes a circle, and notice it's a circle of radius root 2. So we have radius root 2. So something roughly like that. All right, so there's our little slice. So we're spinning that slice around. That's going to form our solid. So to help us understand where phi goes from, we remember that phi equals 0 is going to point straight up, and then we start moving off of here. So what we need to find is this angle. So we say to ourselves, all right, so given that this is at r equals 1, so that says that I have x squared plus y squared, that's r squared, that's 1. So that says 1 plus z squared is 2. That tells us that this corresponds to z equals 1. So this is going through the point 1, 1. So what angle goes off in that nice direction? Pi over 4. So the angle pi over 4. Now, pi over 4, which way? The answer is, doesn't matter. Pi over 4 is just nice. It's like the halfway. So we really are coming off of this direction. So when we come off pi over 4 in this direction, we just barely nick the edge. In fact, what we're really hitting is just the rim, this upper rim. Then we keep hitting our region until we get down to here. What's this angle all the way down? Pi over 2. So pi over 4 is going to be less than or equal to phi. It's going to be less than or equal to pi over 2. Now we have to think about our rho. So rho comes from the origin and it gets out. So it's going to hit, and it's going to keep moving, and it's going to hit again. So where does it hit? It hits at r equals 1, and then it hits at the sphere, which is rho squared equals 2. So we need to translate these into simpler expressions, because I need to have rho equals. Well, rho squared equals 2 is basically done. I just take the square root. So rho is the square root of 2. R equals 1, that's not basically done. We've got to do something. What does R become? Rho sine phi. So rho sine phi equals 1. Divide by sine phi. Rho equals cosecant phi. So we now have that cosecant phi is less than or equal to rho is less than or equal to root 2. So now we're set up. We've got our spherical coordinates ready to go. This part right here, what we've really done is we've determined our bounds. So now we're ready to put it all together and hopefully find something we can actually work out. I hope. I haven't actually done this yet. So we'll find out together whether it's possible. All right. So we start, our density is 2 over rho squared. what does dv become? Come on, you gotta, more lyrical. Rho sine of phi, d rho, d phi, d theta. Yes, good. Now, we just put our bounds in. Theta goes 0 to 2 pi. Phi goes pi fourths to pi halves. And rho goes from cosecant phi, can we do that? Well, we'll find out, up to root 2. Okay, now you'll notice that our density is very convenient. The rho squareds cancel out, almost as if it was meant to be. So when we're integrating d rho, there's no rho. So that makes it a really easy thing to integrate. So 0 to 2 pi, pi over 4, pi over 2. And then what do we get? We get this 2 is left. We get sine of phi. And then we get rho evaluated from rho equals cosecant phi to rho equals root 2 d phi d theta. So 0 to 2 pi, pi over 4 to pi over 2, 2 sine phi, and then we plug this in, we get root 2 minus cosecant phi. Now this might look like, we're going to not be able to make progress here, but the nice thing is that cosecant phi is not as bad as you think. Because remember, there's this 2 sine phi multiplying here. So if you distribute the 2 sine phi through, what do we get? We get 0 to 2 pi, pi over 4 to pi over 2, and then we're going to get 2 root 2 sine phi. Sine phi times cosecant phi is going to be 1. And then there's that minus 2. And now, that's an integral we can do. So we get 0 to 2 pi. Actually, let's just go ahead and do this right away. Let's move the d theta, go all the way out. So we'll have 2 pi, that's the d theta part. And then we'll get this integral. Well, the integral of sine. Well, negative cosine. Then minus 2 phi. Now at this point you should be like, we've made a mistake. That's negative. Mass shouldn't be negative. But maybe we haven't made a mistake because we still have to evaluate. So let's evaluate before we get too paranoid. Okay, so plug in. When you plug in pi halves into cosine, what happens? It's going to go away, 0. 2 times pi halves, well that you can actually do, that's pi. So we get 2 pi times minus pi. So we get 2 pi times minus pi. So that's when we plug in pi halves. And then, actually, we'll just put 2 pi minus pi subtract. Let's plug in pi fourths. Cosine of pi fourths is root 2 over 2 times another root 2 would give us 2 over 2, which is 1, times another 2, so we get minus 2. So that's when you plug in pi fourths. Then 2 times pi fourths will be minus pi halves. Okay, good news. Minus minus comes through, makes all these things positive. So we have a pi, negative pi, and a plus pi half, so we have 2 pi here. So we put those together, we're going to get 2 minus pi halves, and if you multiply that out, we'll end up getting 4 pi subtract pi squared, because the 2's cancel. And that is our final answer, 4 pi minus pi squared. So it did work out. It was nice. What are the odds? Apparently, not 0. That's good. All right. Number 8. Find the integral from -1 to 0, integral 0 to square root y plus 1 of 6 over 1 plus x squared minus y cubed dx dy. Well, I definitely don't want to integrate this function with respect to x or with respect to y right now. That looks terrible. But we're not going to do it yet. We've got to carry out a change of variables. V equals x squared and u equals x squared minus y. Now, how do you do these problems? Well, this is a change of variable problem. What's the clue that it's a change of variable problem? Well, that it says change of variables. Now, the first thing you have to do if you're doing a change of variables problem is figure out what are the change of variables, and here they are. We're going to give it to you. You're not going to have to guess. We're going to say, this is them. And then you're like, okay. Now you actually have to do something with them. So I like to go in the following order. I like to do the Jacobian, figure out what's happening with that. After I do the Jacobian, I like to do the function, update the function as appropriate, and then finally I work on the bounds. So that's what I like to do. I like to go in that order. Jacobian, then function, then bounds. So how does the Jacobian work? Well, the Jacobian, it's one of the most forgiving mathematical things that there is. And, one would hope that your significant other will be just as forgiving in your relationships. So what do I mean by very forgiving? Essentially what you want to do is look at a bunch of partial derivatives. And you look at a whole bunch of them and you sort of string them all together and take a 2-by-2 determinant. So as long as you pretty much follow some reasonable pattern, it'll give you the right thing. So for example, I can say v sub x, v sub y, u sub x, u sub y. You'll notice that I have v's and u's in my rows, x's and y's in my column. Is that the way it's always done? No, the book probably says something different. Will I get the same answer? Yeah, I will. So what do? You take the determinant of this, usually we denote that by a pair of lines, and then technically you take the absolute value. So if you need to make sure that your Jacobian is always positive. Your Jacobian should be measuring how much you're expanding or contracting locally. So we sit down to figure this out. We take our derivatives. The derivative with respect to x is 2x. Derivative with respect to y, 0. That's good. Derivative of u with respect to x is 2x. Derivative of u with respect to y is negative 1. So this would look like negative 2x, but we're taking the absolute value. And here, what do we see? Well, this is interesting. The x is between 0 and root y plus 1, so x is positive. So yeah, definitely we want 2x. There we go. Yeah, good. Now, how do we interpret this 2x? Here's the answer. It's that du dv, r dv du, we haven't picked an order yet, is equal to 2x dx dy, or again dy dx. So essentially, this 2x is telling us how much we scale in between these two different coordinate systems. Now, life would be good if we had a 2x here, but we don't. Now, does that mean we give up? No, it doesn't mean we give up. We're not going to drop any problems. We're going to get all the points. 70 points. None of this, I just need 60 points. 70. That's what we're going for.
Your problem's going to be easy then?
Is my problem going to be easy? I don't remember. Which one did I write? Have I written my problem? I think I wrote my problem. Which one is it? Oh, it's interesting. It's interesting. It's interesting. I like my problem. Yes, it's interesting. Okay. Well, I don't want to give too much away. All right. So, how do we handle this? So here's how you can handle it. There's a couple things you can do. And they work just as well. So one thing you can do is you can say, look, if I put an x there, life is good. But how can you put an x? Well, you divide by an x. And then you update your function. The other thing you can do is you can say, well, look, since I don't have what I need right now, I'll just say dx dy is 1 over 2x du dv. And now you say, well, but wait a second, you're not allowed to have an x here. You're right, I'm not allowed to have an x here. but I can solve for x, and I can write that x is the square root of v. So 2 square root of v du dv. And now I have my change of variables. The dx dy part I can carry out. So that's ready for me to go. So the dx dy, I'm set. 1 over 2 root v du dv, or dv du. We'll figure that out in a second. Let's talk about our function. So now we go through and say, I need to write everything in terms of u and v. Well, there's a pretty clear thing. There's an x squared minus y. So we say, oh, well, that's 6 over 1 plus u cubed. Not looking promising, but okay, we'll deal with it when we have to. So that brings us to our bounds. So let's work on our bounds. So here, what do we have? Well, y goes from negative 1 up to 0, and x goes from 0 up to square root of y plus 1. Now, this curve x equals square root of y plus 1, maybe that's not the most clear. So that's the same as x squared is equal to y plus 1. Or if you like, y equals x squared minus 1. So that's a little bit easier to visualize. So I have this curve y equals x squared minus 1. So it's a parabola that goes down. And now, where does x go from? Well, first off, y goes from negative 1 up to 0. 0 is the axis, negative 1 is the bottom here. And then x goes from 0 to the right-hand side. So this is my shape. So to figure out my new bounds, what I do is I say, okay, let's just take the bounding curves and see what they become. So I have 3 bounding curves. This y equals 0, x equals 0, and then I have this bounding curve here, which I could write that as x squared minus y equals 1. So some of these are pretty easy. X squared minus y equals 1. That translates nicely. That translates into u equals 1. X equals 0. That also translates fairly nicely, because if x equals 0, that's v equals 0. Y equals 0, this one you might have to think about a little bit, but not too bad. If y equals 0, we get that v equals x squared, and u equals x squared. And if we compare these two, we come to the conclusion that u and v are the same. So it becomes u equals v. So in terms of the uv plane, my 3 bounding curves are the straight line u equals v, the axis v equals 0, and then the line u equals 1. So that is the region. That's the only piece that bounds all 3. So there you go. So now what happens? Well, let's put everything together. So integral, we'll figure that out in a second. We have 6 and 2 becomes, I'll say, a 3. 1 plus u cubed, and there's a 1 over root v. Now the question becomes, which order should we pick, du, dv? Would you rather try to integrate 1 over 1 plus u cubed, or would you rather try to integrate 1 over square root of v? 1 over square root of v sounds like a pretty compelling choice. So that becomes saying, let's pick the order dv du. And now that we know the order, we say, okay, where does u go from? U goes 0 to 1. And where does v go from? Well, v goes from 0 up to u. So there's v equals u. All right. Now, I will say that there is a small technical issue which you might complain about, which is this square root of v is going to be really bad at v equals 0, which is over here. And the answer is, don't worry about it. Just keep going. Because it's technically, yes, it's improper, but you do limits, and as long as nothing bad happens, everything works out fine. I will say, by the way, once we get to the end, I'll tell you what the answer that Wolfram alpha gave, and we can compare our answers. So, All right, but we got to get to the end first before we'll see what Wolfram alpha got as an answer. Okay, so here we go. Well, integrating this with respect to v. So really we're going to replace this 1 over square root of v as v to the negative 1/2. So what's the integral of v to the negative 1/2? Sorry, what?
2u to the 1/2 or 2v to the 1/2?
Yeah, okay, so yeah, it'll be v to the 1/2 and then times by a 2. And so we have 3 over 1 plus u cubed, then there's a 2, v to the positive 1/2, the 2 coming from 1 over 1/2. And we evaluate from v equals 0 to v equals u. And as you saw, yes, that is going to become u to the 1/2 because when you plug in 0, you get 0. So what do we have? Well, this becomes integral 0 to 1 of, well, 6 u to the 1/2 over 1 plus u cubed du. Now you're like, okay, do we know how to integrate this? And the answer is you can. Okay, so let's think about this. We're going to put on our Calc 1 hats. And I know it's a little bit rusty, our Calc 1 hats, but we're looking for a way to integrate, and we know, like, look, it's got to be like a substitution. If it's just a Calc 1 thing, there's got to be a substitution to look for. If you don't know where to look for a substitution, just remember there's two places. A function inside of a function, or do you see something that says, oh, that's the derivative I could find the antiderivative of. I don't see clearly a function in a function, but u to the 1/2. Is there some function whose derivative gives us u to the 1/2? Yes. U to the 3/2 would do it. U cubed is actually pretty nice in terms of u to the 3/2. So we're going to make another substitution. W, u to the 3/2. dw is 3/2 u to the 1/2 du. That's supposed to be a 3/2. There we go. Now, if I wanted to, if I multiply what? Well, if I multiply both sides by, say, 4. I could say 4 dw is equal to 6 u to the 1/2 du. So this becomes the integral 6 u to the 1/2 du is 4 dw over 1 plus u cubed, 1 plus w squared. And we've got to update the bounds. 0 to the 3/2? 0. 1 to the 3/2? 1. All right. Now, 1 over 1 plus w squared. I bet you recognize that one. Arctangent. Okay, someone has been hanging around my class. Good. It's arctangent of w. There's a 4 in front, and we're going from 0 to 1. So plug in 1, arctangent of 1. Pi over 4 times 4 gives us pi. Plug in 0, arctangent of 0 is 0. So the answer is pi. Now, I told you I was going to say what Wolfram alpha gave. If you type this into Wolfram alpha, it does pretty good. And it says the answer is 3.14159. But I couldn't figure out that it was pi. And I was like, Wolfram alpha, are you kidding me? It's right there, 3.14159. How can you not just say, it's pi, I don't know why, but it's pi. But, oh well. Well, this is just a sign we can do better than Wolfram alpha, which is good. That means we can keep our jobs as engineers, if we can beat the machines. When we start to lose to the machines, we're in trouble. So now we're going to do a transition. We're going to switch to sort of the different part of the course. This is the vector calculus part of the course. So we'll start by saying number 9, find both divergence and curl for the following functions. Now when you see divergence, that means divergence of a function f, that's your del dot f. And that means you're taking the partial derivatives of each entry. The curl of f, that's del cross f. And that's when we do our cross product. Now note, you might be given functions in two different ways. So we've seen both notations here, where you have something times I plus something times j plus something times k, or as a vector, and you have the three different entries. So let's start with part A. So we'll start with del dot f, that's our divergence. So what you do is you go through each entry and you take the derivative with respect to x in the first entry. Well, that's cosine of y e to the x. Then you're going to add the derivative with respect to y of the second entry. There is no y. 0. Okay? Then you're going to add the derivative with respect to z of the third entry. Well, derivative of tangent is secant squared. And there's our divergence. So we're a fourth of the way done. To be fair, the divergence is oftentimes faster. Now, be careful. When you're doing a divergence, you should end up with a function. There should be no more vector. It should be a function. Now the curl, well, that's going to take a little bit longer. So you write down your I, J, K, give yourself space. I probably haven't given myself enough space. I'm going to regret it in a second here. Partial x, partial y, partial z. Remember, that's what del is. Del is the set of partial derivatives. And then your f goes in the last row. So cosine of y e to the x, and then there's x squared z cubed, and then there's y plus tangent z. So now just be careful and work it out. So I partial y of y plus tangent z. So I'm taking the derivative of the last piece with respect to y. That gives me 1, and that's in the I direction, so 1i. J partial z of cosine y e to the x. Well, there's nothing there because there's no z. So that says that's a 0, 0j. K partial x of x squared z cubed. So the derivative with respect to x would give us 2x z cubed, and that's in the k direction. So that's going what I would call downhill, going uphill. So we're going to take the derivative with respect to y of cosine y e to the x, and that's with respect to k. So the derivative with respect to y would be minus sine y e to the x. Now, because we're going in the uphill direction, we're going to subtract that derivative. So minus becomes a plus. All right, that's k. Then the next term, we're going to take derivative with respect to z of x squared z cubed. And that's going to be in the I direction. So that will give us 3x squared z squared I. And finally, we're going to have y plus tangent z, and then we're going to take the derivative of that with respect to x. Well, there is no x, so it's 0. And that's in the j direction. We're going to subtract it. And I forgot I need to subtract that one as well. So it turns out that we get the following. We get, if we write it with the ijk notation, we'll get 1 minus 3x squared z squared I. Nothing in j. And that's okay if you don't have anything in j. You don't have to. There's no requirement that says you have to. Plus 2x z cubed plus sine of y e to the x in the k direction. Okay, so that's part A. So there's not a lot to this problem. It's just a matter of carry out the computation, do the work. And let's do part B. We're going to have to pick up the pace at this back 5. Well, don't worry. The back 5 go quick. They're very fast. So for part B, again, del dot g, take the derivative with respect to x. In the first entry, that would give us 2x over x squared plus y squared plus 1. Derivative with respect to y in the second entry is 1 over y squared plus 1. Derivative with respect to z in the third entry is sine of xy. And there's your gradient. There's your divergence. Divergence is great. You kind of hope for it. In fact, we have this beautiful theorem called the divergence theorem, which is going to be our last topic. And when you get to it, you should have said, why did you say this for the end? This is so beautiful. You should have done this on day 1. We wouldn't have understood anything, but it's so beautiful, we could have at least thought about it for 4 months. Okay, so del cross g, I, j, k, partial x, partial y, partial z, log of x squared plus y squared plus 1. And then the next term, arctangent of y plus z cubed. This is why you have to give yourself space. And then z sine of xy. So we take partial y of z sine of xy. Okay, there's a y there. So that's going to give us a xz cosine of xy, and that's in the I direction. Partial z of the log of x squared plus y squared plus 1, nothing there, 0j. K, partial x, arctangent y plus z cubed, nothing there, 0k. Now going uphill, partial y of log of x squared plus y squared plus 1, there is something there, so that's going to be a 2y over x squared plus y squared plus 1 times k, but I put plus I shouldn't have because it's uphill, so it's minus. Partial z of arctangent of y plus z cubed is 3z squared. That's in the I direction. And we're going uphill, so subtract 3z squared I. And finally, z sine of xy, we're going to take the derivative of that with respect to x in the j direction. So that's going to become a minus. When we take the derivative of that with respect to x, we'll get a yz cosine xy in j direction. So we end up with xz cosine of xy minus 3z squared, comma, minus yz cosine of xy, comma, and then minus 2y over x squared plus y squared plus 1. So these problems, again, it's just do the computations, be careful, and you'll be fine. All right. So let C be the curve t comma t squared with 0 less than or equal to t less than or equal to 1. Find the integral along the C of y plus x squared dx plus e to the x squared dy. This is a line integral. How do we know it's a line integral? Because we see an integral along C. Now, generally speaking, there's a couple of types of line integrals that you might encounter. One integral is if you see an integral of f of xy ds, which is, this is very faded, but okay, yeah, it's showing up. For this one, you have to go through and basically pull out your arc length formula, and then life is good. It's really, cross your fingers, hope that whatever your ds is works out nicely, but we'll either ask you just to set it up, or we'll give you something that does work out fairly nicely. The other type of line integrals you have is you have two flavors. So you have the integral of, I would call it mdx plus ndy. And it's this, the two flavors are not that there's two different forms. This is the one form. It might be expressed in two different ways. For example, sometimes we call it mn dot dr. And this is the integral that you saw if you're doing things like finding the amount of work done moving an object. You have a force, and you move along the curve. So when I'm saying there's two different flavors, the two different flavors are the following. And I'll actually change to a more legible color. So the two flavors are, one, you have something that's conservative. And if it's conservative, this is the woohoo, life is good, because conservative ones are easy. Or you have things which are not conservative. Now, which one are we in? Is this conservative or not conservative? Now, if you're not sure, try to make a conservative function. And the way you could do is you could say, well, if I integrate this first term with respect to x, what would I get? Well, I'd get xy plus 1/3 x cubed. Now, integrate this second term with respect to y. You get e to the x squared times y. Are these compatible? And they're not, because there's pieces that involve x and y over here which aren't showing up over there. So this is not conservative. So when it's not conservative, what do you do? And the answer is put everything in terms of your parameterization. And that's one of those words which I can never say out loud. And I can't really spell it either. But so what you're going to do is you're going to put it and use your parameterization to figure out what to do. It's easier for me to explain it. So when I talk about using your parameterization, you have that the integral along C becomes integral a to b. You have your x becomes x of t. Your y becomes your y of t. Your dx becomes x prime of t. And your dy becomes y prime of t. And then add a dt on the end. And that's how you do it by parameterization. You just translate and say, look, I'm going to do everything in terms of the parameterization. So that's our only choice because it's not conservative. If it is conservative, you've got more options, which is why we love conservative ones. So here, our x of t is t, and our y of t is t squared. So we're going to have our integral becomes 0 to 1, because our integral c becomes our integral for our bounds. Our a and b are given us in terms of where t starts and stops. Now we have y plus x squared. So y is t squared. X squared would be t squared. Dx is 1. Plus e to the x squared, so x is t, and then square it, times your dy, which is 2t. And now we tack on a dt on the end. So if we're ever given an integral that we can't do by being conservative, we can always do this. And we just have to hope that we can actually integrate this expression. And it looks pretty promising. If we clean up a little bit, that's 2t squared plus 2t e to the t squared. And both pieces, I think, are integrals we can do. The integral of 2t squared, that's 2/3 t cubed. Now this integral looks a little bit daunting, but we say, oh, wait a second, that's just a simple substitution. If you let u equal t squared, you get du as 2t dt. So this is e to the t squared. And then you're going to evaluate from 0 to 1. So this becomes, plug in 1, 2/3 times 1 plus e to the 1. Subtract, plug in 0, 0 plus e to the 0, which is 1. So we end up with e, then 2/3 minus 1 is minus 1/3. And there we go. Okay, so those integrals aren't too bad. And normally speaking, if you have something that's not conservative, the curve is going to be super, super easy. So if you see a super easy curve, you're like, oh, this is probably not conservative. Let's just integrate it straightforward. Then you're probably thinking, what do you mean by a curve that's not super simple? So suppose we look at the next problem. So here's this curve, and it's actually shown what the curve is. So we have time goes from 0 to pi over 2, and our curve is 2 cosine t plus 1 over 10 sine of 20t, and then sine of t plus 1 over 10 sine of 20t. And that's the actual curve. That's not just like I drew a random squiggly line. This is the real curve that starts at this point at time 0 and ends at this point at time 1. There's a little tiny arrowhead right there. So the problem says, okay, find the integral along this curve of this function. Well, this curve is not a nice curve. So if you don't see a nice curve, you say, I want that conservative option. Because the conservative option says, I just need to know what's happening at the endpoints for my potential function. So let's first figure out what the endpoints are. So this endpoint, that's our start. That's at t equals 0. So to get the endpoint, plug it into your function. So the nice thing about 0 into the sine function gives you 0. So you're going to end up 2 times cosine of 0, which is 1. And then sine of 0 is 0. 2 times cosine of 0 is 2. So this is at the point 2 comma 0. That's where we start. Where do we stop? We stop at t equals 1. So you plug t equals 1. Not t equals 1, t equals pi halves. 1/2 pi. That's what I meant to write, of course. All right. So t equals 1/2 pi. We still have a sine of 10 pi. That's still 0. So these terms go away. Cosine of 1/2 pi is 0. And sine of 1/2 pi is 1. So we end up at the point 0, comma 1. All right, so we go from 2, 0 to 0, 1. So our hope now, this is conservative. So we say, all right, let's take the integral of this with respect to x. And if we did that, we'd get y e to the x minus x squared. Take the integral of the second one with respect to y. And if we did that, we would get y e to the x. And then here, 2y over 1 plus y squared is natural log of 1 plus y squared. And what we see is that these are compatible. In other words, the parts that involve both x and y showed up in both. So our potential function should be the following. F of xy would be, as minus x squared plus y e to the x plus natural log of 1 plus y squared. Now, to be sure, we'll do a check. Gradient of f would be minus 2x plus y e to the x, comma, and then derivative with respect to y would be e to the x plus 2y over 1 plus y squared, and that matches what we have over there. So if you're going to just sort of write it down, at least check your answer, because we will want to say, okay, did you actually know that? Were you maybe glancing at somebody else's test? We don't want to say that you did, but we want to make sure you're doing it, not just randomly coming up with things. We want to make sure you know the processes. Okay, now we're almost done with this problem, believe it or not, because we haven't written down very much. This problem looks complicated, but the thing is, once you have the tools, complicated problems become less complicated. Almost easy. So what happens is that this integral becomes the function, our potential function. We evaluate, we take our endpoint, 0, 1, subtract our start point, 2, 0. So this is the function at 0, 1, subtract the function at 2, 0. When we plug in x equals 0 and y equals 1, well, we're going to get 0, and then we're going to get 1 times e to the 0, so that's 1. Then we're going to get plus log of 1 plus 1, so that's plus log of 2. Subtract, plug in x equals 2, y equals 0, we'll get negative 2 squared, so that's negative 4. Then we're going to get 0 times e squared, well, that's 0. Then we're going to get log of 1 plus 0 squared. Well, that's log of 1. That's 0. So 1 minus minus 4 is 1 plus 4 are 5, and then plus natural log of 2, and we're done. That's our answer. It worked out pretty well. Almost too well? No. It worked out the right amount of well. Okay. Number 12. Let R be the region in the plane consisting of a 2 by 2 square centered at the origin with semicircles of radius 1 glued on each side. So what's happening here is that there's this sort of 2 by 2 square which hasn't been drawn in, so we'll add it into our picture. So I have this 2 by 2 square here. All right, so there's the shape. It's a square and 4 half circles glued to the sides. And then C goes around the boundary of this shape. And it's going to go around in a counterclockwise direction. That's going to be important here. So the problem says, find the integral along the curve of sine of 2x plus arctangent of y dy minus 4y squared sine squared of x dx. Now, generally speaking, whenever you see an integral that looks really bad, you should ask yourself the question, am I supposed to be doing this integral? A lot of the time, the answer is no. You should not be doing this integral. You should be using the tool. What's the tool that applies here? Green's theorem. So what we have is there's this region. And this curve, it's a closed curve. So a big clue for Green's theorem is if you see something where you have an integral along a closed curve. That's a good clue that this is a Green's theorem problem. The other thing that's a good clue is look for things that are like, there's no way they want us to integrate it. And then that is correct. We do not want you to integrate this because we want you to do something else. Green's theorem. Okay, so we have this region. Our orientation is the correct orientation. So what we can do is we can say, hey, this becomes the integral over our region R of, and now we've got to be careful here, because Green's theorem says the following. The integral around our curve of m dx plus n dy is equal to the integral over our region of, n sub x minus m sub y dA. The only thing you have to be careful of is your orientation. And remember how the song goes. To the left, to the left. When you walk the curve, keep the region to your left. Right? That's the song. There's an orientation. Okay, so what's the part to be careful of here? See, they laid a trap for us. They put the dy and dx in different order, seeing if we were going to pay attention. Oh, those crafty people. But we're not going to fall for their trap. So the thing is that what's ever in front of the dy, we're going to take the derivative of that with respect to x. In particular, that arctangent of y, gone. Oh my gosh, getting rid of an arctangent? I know. It's not like me, but, you know, mix it up sometimes. Derivative of sine of 2x is 2 cosine 2x. Okay, then we go and say, all right, whatever is in front of the dx, that's the m dx, we're going to take the derivative of that with respect to y, and we're going to subtract. Okay, so we're going to subtract, and here it'll be 4 sine squared of x. And, whoops, we're going to subtract, actually there's a negative because there's already a minus here. So minus a minus. And we're going to do that dA. Okay, so minus a minus makes this into a plus. Now we're like, oh, but we actually have to integrate that? Well, let's think if we can improve it. How do we actually integrate sine squared of x? Power reduction. Sine squared of x is 1/2 minus 1/2 cosine of twice the angle. So, if you carry out the power reduction, this becomes the integral over your region of, there's that 2 cosine 2x, and if you follow all the numbers through, you get a plus 2, and then you'll get a minus 2 cosine of 2x. Well, the 2 cosine of 2x's cancel out, which means that what we're integrating is 2. But we can just pull that out. So that's 2, integral of your region, dA. But we can do that integral without doing any integration. That's just 2 times the area of our region. So we look at our region and say, okay, how much area is there? Well, there's a 2 by 2 square. That has area 4. But then I can think of it as there's sort of 2 half circles, or if I like, I can just imagine putting 2 half circles together, making 2 whole circles. Each circle is radius 1. So each circle would give us pi. So there's 2 pi among those half circles, giving us a final answer of 8 plus 4 pi. And that's it. So it pays to pay attention. All right. That leaves us with 2 more. And you're probably thinking, wait a second, you've reached the end. But there's still more because we have to learn something, one more class. So this is that one more class. And I'm still going to cover this, so I'm going to try to explain things as we go on. So here we go. You've recently been hired to help design rides in an amusement park. One of the rides that you're working on involves a large bowl-like surface. In particular, the surface is given by 1/2 times x squared plus y squared, where 0 less than or equal to z less than or equal to 2. Everything's measured in meters. You're working to ensure the supports in place will be sufficient to support the weight. In particular, the design calls for the density to increase with the height. So density of xyz is z kilograms per meter squared. Find the total mass of the surface. So we're after looking at the mass of the surface. So this is something called a surface integral. And you might think, what's a surface integral? Well, imagine a line integral, but replace the word line with surface. That's a surface integral. And what's happening is you have this surface out in 3-dimensional space. So I have here, there's this surface, and we're going to focus on a very special type of surface. Z is a function of x, y, and it's over something here in the xy plane, and we're going to call this a region R. So z equals f of xy over R. And what we want to do is we want to say the following. I want to find the integral on the surface. So we're going to let G be our surface. I don't know why we do this, but we often do. I guess, G for Gerfus. I don't know, but all right. The problem was we already used S for solid. So we don't want to use S for surface. That's just going too far. So the integral over the surface of some function g of x, y, z, d, and I call it SA. So the idea is what we do is we take our surface and we slice it up into little teeny tiny pieces. So there's a little tiny piece of my surface. And I say, all right, I have my little piece of my surface. The contribution from that piece is g of x, y, z times that little area of that piece, and then I add them all up over all the pieces my surface creates. How do you do this in practice? In practice, it gets kind of bad. So you integrate over your region of, what you do is g, x, y. What is z? Z is f of x, y. And now, what's your DSA? Well, that is a little piece of your surface. It's a little bit of surface area. So you go back to your surface area formula. 1 plus f sub x squared plus f sub y squared dA. So that's a surface integral. All right. So let's actually do this. So we're going to find our mass. And the way you find mass is you always do the same thing. You integrate density. Doesn't matter what setting. You always say, look, mass is the integral of density. So for us, we say, all right, what is that? Well, it's the integral on our surface. Our density we're given is z. So we integrate on our surface z. So now we say, all right, there's something else. We have to say, we're told that z equals a half x squared plus y squared. So this particular surface is actually pretty nice. It's a bowl. It's kind of a shallow bowl. That's probably going to be to our advantage. So it's a shallow bowl. But we know that z goes from z equals 0 up to z equals 2. If we were to take this bowl and to cast its shadow down, so in other words, imagine looking at it from above, we would see that it would correspond to this region here in the plane. What region is it? Well, when z equals 2, we would come up here, we would have 2 equals a half x squared plus y squared, or x squared plus y squared equals 4. So it's the region here, this region R, this is a circle of radius 2. So this is going to become the integral over R. Z becomes 1/2 x squared plus y squared. Then we have the square root of 1 plus f sub x is x. We're going to square that. F sub y is y, because there's 1/2 times 2y. So that's y. We're going to square that dA. So that's what we have to integrate. Now, you might say, that does not look fun to integrate. You are correct. It is not fun to integrate, at least not if you're using the wrong coordinate system. But we're going to use the right coordinate system. What's the right coordinate system? Polar. Because x squared plus y squared. We see our region is a circle. So what's happening is we're taking our surface and we're basically pushing it down into our plane. And we're working on something which will give us the same answer as a region in our xy plane. So we say, okay, so this is going to be integral. 1/2 x squared plus y squared becomes 1/2 r squared. Then this becomes the square root of, here x squared plus y squared again becomes an r squared inside the square root. dA becomes r dr d theta. Theta goes 0 to 2 pi. And then r goes 0 to 2. Now, notice there's really nothing on the inside about d theta, so I can push the d theta all the way over, so that's just going to give us a 2 pi. How do we actually do this integral? Well, I won't hum and haw too long because there's one more problem after this which is even more interesting. So what we do is substitution. That u equal 1 plus r squared. Then du would be 2r dr. Or I put this 1/2 across. So this integral 0 to 2 pi of d theta becomes a 2 pi in front. Then once we make the substitution, 1 plus r squared, our bounds will become 1 to 5. Because when r equals 0, u equals 1, r equals 2, u equals 5. The 1/2 stays at a half. R squared becomes u minus 1. Square root of r, 1 plus r squared becomes u to the 1/2. And then the r dr becomes another 1/2 du. Now, this is a doable integral. We can cancel off one of the halves. We can pull out the other half, so we get pi over 2, integral 1 to 5 of u to the 3/2 minus u to the 1/2 du. So this is pi over 2, and then we have 2/5 u to the 5/2 minus 2/3 u to the 3/2. Evaluate that from 1 to 5, which leaves us with pi over 2 times 2/5 times 5 to the 5/2 minus 2/3 times 5 to the 3/2. Subtract 2/5 minus 2/3, and that looks pretty simple to me, so we'll stop there. All right, good. That brings us the last one. All right, now this is a different kind of surface integral, so you got to be ready for both types. Now, normally surface integrals are terrible because they have that square root involved, and the square root is a really, really terrible thing. But there's a really cool special case, and that is when you look at what's called flux. This is fancy Latin for flow. So we think about things moving, electrical flow, fluid flow, air flow, all kinds of flow. So the idea you have is you have the surface G sitting somewhere out in space, and you have flow. In other words, things are moving. So you have things which are moving through the surface. And the question becomes, okay, how much is moving through the surface? And in which direction? So what's the net flow? Now, the way you compute it is you do a very special type of surface integral, but here's the really cool part. Now, if you have the following setup, so you have the z equals f of xy, that's your surface, over some region R, and your oriented surface is pointing up. So what this says is that we really want to make sure we're dealing with surfaces where we have a top side and a bottom side. So it's just saying, okay, look, we know which side is up. Then we can compute the flux of a vector field, and this is a vector field here. And so the flux of the vector field M and P through our surface is given by the following equation. You find the integral over your region of minus m fx minus n fy plus p dA. See, it's the same idea before in that, oh, what's happening is we're really, instead of working on the surface, we're saying, boom, push down into your region R. The thing that makes it nice is we got rid of the square root. And inherently, the reason why we got rid of the square root is because of our normals. The normals actually have something that look like the same expression, and the two square roots cancel much like they did before. So for us, our m, n, and p are giving us sine of 2x minus x squared, e to the xy, and 8xy. So what do? Well, here, this x plus y cubed, that's our function f of xy. So we have all of our pieces in place. We just need to put it together. So let's look at our region. We'll write it down for reference here. So our region has the following. We have triangle, it's 0, 0, and at 1, 1, and at 0, 1. So we have our region is this shape here. Okay, so we are looking for the flux will be the integral over this region of minus m, so that's sine 2x minus x squared times f sub x. F sub x is 1, so times 1. Plus, minus n, so minus e to the xy times f sub y. Well, the derivative of f with respect to y, 3y squared. Then plus p. So plus 8xy. And then we have to do this dA. So what do we have? We have really 3 integrals, and we have to work through them one at a time. And it's perfectly fine to do the 3 integrals separately. So let's go ahead and work through them. So let's start with the first integral because, well, it's the first integral. Why not? So we want to integrate negative sine of 2x minus x squared. And now we have to make a choice. Do we integrate first with respect to y or with respect to x? Well, the answer is we're not going to integrate that with respect to x. Hopeless. So we better integrate with respect to y and then with respect to x. Now from our picture, x goes from 0 to 1. And y, well, we go from the line y equals x. So that's x up to y equals 1. X to 1. So this becomes integral 0 to 1 of minus sine of 2x minus x squared. And then when we integrate with respect to y, we're going to get a single y. Evaluate that from y equals x to y equals 1 dx. So that becomes integral 0 to 1 of minus sine of 2x minus x squared. And then we're going to get 1 minus x dx. Now we say, cool. Can we integrate this? Well, if we put on our old Calc 1 hats, pretty reliable, 2x minus x squared. If that's our u, then this 1 minus x, what would it be? Well, 2 minus 2x is du. So this actually, whole thing here becomes a half of du. We lose a factor of a half, but that's not so bad to lose a factor of a half. So if we make that substitution, that will become integral 0, let's check. 0 minus 0, okay, still good, still 0. Plug in 1, get 2 minus 1. Oh, still 1. Oh, okay, so it's still 0 to 1. But we did check the bounds. We plug in x equals 0, u equals 0, x equals 1, u equals 1. All right, then we get minus 1/2 sine of u du. The 1/2 coming from there. So the integral of minus 1/2 sine of u is 1/2 cosine of u. Evaluate that from 0 to 1. So that's 1/2 cosine of 1. And then it's going to be minus 1/2. So that's the first piece. All right. Now let's do our second piece. Number 2. So number 2. Let's see what we can do. So we have e to the xy 3y squared. Now the question is, what do we want to integrate with respect to? If we integrated with respect to y, lots of integration by parts ahead, so let's not do that. So here we'll actually integrate in a different order. And are we allowed? Absolutely we're allowed. So we're going to integrate minus e to the xy 3y squared, and then we're going to integrate dx dy. Y goes from 0 to 1, and then x goes from 0 out to x equals y. So 0 to y. So this becomes, well, if we integrate, we're going to get integral 0 to 1. And here, integrating with respect to x, we're going to have to divide by a y. So we're going to get minus 3y e to the power xy. And then we're going to evaluate from x equals 0 to x equals y, dy. So this becomes integral 0 to 1. Plug this in, minus 3y e to the y squared. Plug in 0, you get minus 3y e to the 0. Also known as just minus 3y. All right, dy. Now, these are pieces we can integrate. Minus 3y, no problem. But even the minus 3y e to the y squared, still no problem. Why? Well, because think about the substitution. If u equals y squared, du will have a y in it. In fact, this will turn out to be minus 3/2 e to the y squared minus 3/2 y squared. So if you go ahead, you can double check, take the derivative. You get minus 3y there, and here you get minus 3/2 e to the y squared times 2y, that's minus 3y. And then we're going to evaluate from 0 to 1. So you plug in 1, you get this is minus 3/2 e, and then you're going to get minus 3/2 times 1. Then you're going to subtract, plug in 0, you're going to get minus 3/2 times 1 and minus 0. Well, the nice thing is, minus minus, those become plus. Minus 3/2 plus 3/2, those actually cancel. So you're left with minus 3 over 2e. Nice. So that worked out really well. Now we come to our last layer. Well, okay, which one is that? The 8xy. So how are we going to integrate that one? Well, really, there's no surprises here. It's like, well, it doesn't really matter. And since it doesn't matter, let's do dx dy. And the reason I point there is there's 0. And whenever you can get a 0, do it. So we have integral 0 to 1, integral 0 to y, 8xy, dx dy. Well, okay, that's integral 0 to 1. Integrate with respect to x. That'll be 4 x squared y. Then we're going to evaluate x equals 0 to x equals y. And then we're going to evaluate that dy. So when you plug in 0, 0. Good. Plug in y, well, you get 4y cubed. So this is integral 0 to 1 of 4y cubed dy. Well, that's y to the 4th, evaluated from 0 to 1, which is 1. So if we put this all together, well, we'll have a half cosine 1 minus a half, and then minus 3/2 e, and finally plus 1. So 1/2 cosine of 1 minus 3/2 e, and minus a half plus 1 makes plus 1/2. Just as you would have expected. And that's a nice way to finish up. Of course, it's a little bit, maybe a little bit more challenging necessary than we would have wanted, but this illustrates another idea. It says, hey, if you have multiple parts, you're allowed to integrate them in different ways. So be prepared. Say, look, maybe I should separate them into different parts, and each part I'll do in a different way. Perfectly fine if it helps you, and really our goal is to get the answer, so do what it takes to help you get to that point. Good luck. Good luck on that exam, and I hope you do well. Bye. Because I did make a small mistake on the last problem, and I know I make small mistakes on a lot of these problems, and I'm trying to make fewer of them. So I made a mistake in this part. So I just want to say, let me correct that mistake really quickly. So the good news is it's a small mistake. I would have only lost like 1, maybe 2 points if I had a harsh grader. So still would have passed. All right. So what was my small mistake? So let's go to here. You have the integral 0 to 1 of minus 3y e to the xy. evaluated from x equals 0 to x equals y. And then we're doing that dy. And so here we go. So you plug in x equals y. And what do you get? Well, you get minus 3y e to the y squared. And then we're going to subtract, plug in x equals 0, which is minus 3y. So my mistake was I forgot this extra minus, because if you look here, that was just a minus 3y. It should have been a plus 3y. So you work it out. The rest of it's the same way. So minus 3y e to the y squared plus 3y dy, which becomes, well, you integrate this. That'll be minus 3 halves e to the y squared. This is plus 3 halves y squared. And we evaluate from 0 to 1. And so we get minus 3 halves e plus 3 halves. And we're going to subtract, plug in 0, minus 3 halves plus 0. And minus minus makes plus. And in particular, these don't cancel, they combine. So you end up with minus 3 halves e plus 3. Which means, because I said minus 3 halves e, the correct answer needs plus 3 more. All right, so that's the correction. Just want you to know, in case you're like, it seems wrong. Well, it was wrong. So that explains that. All right.